It gives me great pleasure to welcome our speakers for this afternoon, Federico Boschetti from Pisa and Bruce Robertson from Mount Allison, who are going to be talking, I think, about a very important topic, the optical character recognition of Polytonic Greek.
Thank you so much. I'm going to begin. I know Federico and I are most gratified to be welcomed here and to a seminar whose topics we've admired from afar. And we're doubly gratified that you gave up what promises to be one of the most beautiful afternoons probably anywhere in the world. we'll aspire to make it up to you with an engaging talk. So we are talking about the optical character recognition of Greek, turning the image of Greek text into a digital text that we can work with. And this is a major effort, one that our commercial packages and even up until recently open source packages have not done very successfully or successfully at all. Why would we wish to do this? It's an important question because the motivation, the end product, as so often in digital humanities, determines the pipeline that's going to get you there. One of them, the one that we're going to focus on, because the partners that we're working with are so interested in this, is the much more rapid digitization of Greek texts not yet available in an open format. We may have the TLG, but working with it using big data tools is not as practical as it might be. But you might also want to study textual variants and the app crits available to us. You might want to think about text reuse analysis, plow through journal articles for Greek that would tell us what the journal author is citing and quoting. Or you might want to be able to do general purpose OCR search like we enjoy in Google Books. Well, which of those uses we have in mind determines the kind of processes that we need to have at hand. Digitization in particular, the idea that we want to have a high quality digital text to work with, means that we both need to do manual editing and the best that we can do on the automatic side of things. Because when we go to manual editing, we want it to be just tickety-boo, and then some bright young thing is going to make it even better. Some of these other processes, though, might not require those pipelines to be engaged, and we can get away with other processes. But in this case, we're looking at digitization, so we're going to talk about an automatic pipeline that gets the text to a certain point, and then we're going to move to the process of editing by hand, which is Federico's bailiwick. So generating the data that will be worked on manually is our topic, and why is it a challenge? Well, for those of you who don't work with Polytonic Greek, first of all, the letters are funny, but that's not necessarily that much of a challenge. But we also have very small additional marks that come in here. We have the accents, the breathing marks, and then even under the character, we have positioned from time to time iota subscripts that are important for our understanding of the text. So the accentuation comes all around, well, not all around the character, but above and below it. And these can interact with the characters in interesting ways. At least as challenging is the fact that the 19th century texts that we would aspire to work with are quite diverse. Here's a sample of 3 that I've processed. You start to sort of notice national bases for the different fonts, and they're all beautiful in their own way, but they are very different from the point of view of a computer. Here's 4 others, which again, if you just cast your eye over them, you'll see that while 1 and 4 look fairly similar, when we take into account the ones before, there's a lot of diversity. We're used to things like, those of us who work with Greek are used to things like lunate sigmas. We sort of get the flavor of a text pretty quickly, but a computer needs to be taught these things, and they can be difficult. The fact that accents appear above and below characters and the fact that authors or publishers often want to get as much text on a page as possible sometimes means that while the human eye can make a line, understand a line of text fairly well here, it's difficult for a computer. So the second challenge that we face is or the third rather, is the process just of recognizing the lines. Because if you don't know where the line of the text is, the computer will recognize each of the characters just fine, but will make them into a kind of soup. A little bit like when our students translate poorly and they just sort of go, well, I don't know, there's a wine and there's a boy and there's a flask and I don't know what's happening. So you can see that one process you could do here is to draw a line where there's a clear space between the two. There is no such thing in this text. And so one of the most commonly used tools for line separation in OCR is often not available to us in Greek. And when you're trying to decide which way should an accent go on the line above or below, it can be difficult for a computer to know how to do that. Another challenge that we face, and every OCR endeavor faces, but it's particularly troublesome when we have these tiny little graphical symbols, is binarization. Every OCR engine works on a black and white picture. So even if you start with a color one, eventually you have to turn it into, is this text or is it page? But when you start with an image like this beautiful page here, and you can see that it's stained up in the upper right-hand corner, in the left corner it's rippled a little bit, causing shading on it. Most commonly, shading is caused by the gutters of texts when they're put on a stand for image, for photographing. What will happen is you'll get parts that are darker than others. So at a given binarization threshold, this particular text in the top right, I believe, comes out fairly dark so that the acute accent over this epsilon is combined with it. It's not necessarily a problem. But then on the same page elsewhere, you have characters starting to split apart into different little bits and pieces, not a whole character. None of these are necessarily fatal problems, but but you wish you could find one particular threshold that would be perfect for a given page. Alas, that's not going to happen because of this shading. And I can tell you also, even if the page were perfectly similar, the whole page were the same darkness, a computational process to find the perfect threshold for that is not to be found. The best method, called the Otsu method, still is error-prone. This is a graph that shows how Greek the page result is for 3 pages. And on the right hand, that's the y-axis, is how Greek the page is. So you can think of the y-axis as goodness, right? And the x-axis is how dark we made it, how we turned up the contrast on the TV screen. And you can see for 3 adjacent pages, this graph has different curves for each page. And we can imagine that page 33 in particular, we'd want it to be much lighter. We'd want it to go all the way over here probably. For page 35, we found the peak, and so on. So this is a tough issue which we have to face, the binarization of the text. What are the resources that we have on hand to work on this problem? Well, one I've already used. To make that graph of contrast of darkness threshold versus Greekness, I used Dr. Boschetti's Greekness Index, a little digital tool that tells you how Greek a page of text is without it having a ground truth document to pull on. It's not just based on a dictionary, though that's kind of the gold standard. If a word is in the dictionary, then it gets scored quite high, but also on likely sequences of letters, and he'll be explaining this or a similar process to this later on. But in my slides, I just call it a B score, so you'll now know that that means just how darn Greek something is. Well, another tool that we have, or another resource, is archive.org. Much better than Google Books. It provides thousands of volumes rendered in higher resolution, not 300 dpi, but 400 plus, color images, so we can do our own binarization, and they provide OCR results from Abbey Fine Reader. Now these aren't usually done in using a Greek classifier. When they do, the Greek is quite poor. But they provide excellent Latin script recognition when they use Latin. We'll see that this can be important later on. And they provide the top quality line segmentation that we were craving when we saw that problem with drawing that line. So this is a commercial package, but its results are provided to us on any book from archive.org. And then we have open source OCR engines. I'm working on Gamera, which originally began its life as a music recognition package, but it's quite versatile. Nick has been working on Tesseract and doing great things with it, and this is an exciting development. He's getting good results by working down in the C++ and everything else. And Dr. Boschetti has shown, even more excitingly, that OCR Opus, which many of you might have thought was a somewhat stalled project, well, it has kind of resurfaced, and it is able to use the Tesseract training sets, the rules that one gives an OCR engine so that it can figure out what it's doing. It's able to use those to do its own work. So we have 3 different engines, which is a really exciting development. We also have an interchange format. The developer of OCR Opus, or Opus, has devised a HTML variant called HOCR, which tells us where words are by means of the title attribute. This is the bounding box of this particular character on the page. So you can both view this just as HTML on a browser, but then you can also process it like it's XML with lots of cool stuff that you can extract from it, turn it into déjà vu, or align different texts to each other. Okay, so those are our resources. This is the problems we want to get to. How are we going to do it? Well, we're going to spend a lot of time with this flowchart. This is the process I've developed through my sabbatical. And really, I'm meaning to blow you away here. I know the font's too small. We're going to go through each of these steps actually in about 5 slides, but I want you to notice that we're going up here, up to the output. We're starting with the raw OCR, one might say. We're doing a process called blending, which takes a whole bunch of output for a single page image and comes up with one best page output for that. Then automatic OCR spell check to be distinguished from manual spell check that has a human attached to it. And then the process of combining Latin source and Greek source, if that's possible. Let me show you those one by one. Producing the raw OCR output we're doing right now with Gamera. I've made a plugin for Gamera so that I can import the high-quality line segmentation information from Abby's fine reader's output. This compensates for Gamera's poor results in its critical function. I've also made a plugin to output HOCR rather than just plain text, so that these different pages can talk to each other about where the words are on the page image. And lastly, I made a wrapper function that generates a range of output pages, HOCR pages, based on binarization threshold. So imagine turning up that contrast dial and getting an output OCR page for each time you click it forward one. It'll be bad, better, better, ideally great, and then worse and worse. We typically produce about 10 to 20 of these. But we don't want them all, we just want one best page of text output for every page input of image. And that's what this step does. This I call HOCR blending. First, we take the Boschetti score for each of these darkness pages. We select the highest ranking one and use it as the basis for the next step. The next step is to look through each Greek word in that page and say, are you in the dictionary? If you aren't in the dictionary, then look through all the other pages to see if the thing that's in that same space on the page, same physical space in the image, is a dictionary word. Because maybe the best page, despite being the best page on average, has a dark corner which will get a better word result at a lighter threshold. So the idea is to blend all of these results and get one best page that has the most dictionary words in it. Once we have those for the entire volume, and this is done in a high-performance computing environment with 40 cores, once we get that for every volume, we reduce all of those pages to unique strings, and we do an automatic spell check process on it. This uses a weighted Levenshtein spell checker that I've used the Levenshtein package for Python and then done the weighting sort of myself. We have a weighted edit table that is handcrafted for every font and sort of Greek in general, and a big dictionary. The dictionary now is more like, what, 3 million words or something like that, thanks to Professor Boschetti. So the weighting table indicates which edits are preferable or even allowed. And in particular, it tries to deal with very light edits, very likely light edits, like a smooth breathing mark being misidentified as an acute accent. If you get 2 smooth breathing marks in a row, it may well be smooth breathing with acute. The weighting table looks a little bit like this. Here's one for Lunate fonts. I'm kind of cheating here, but what I'm saying is, if you see a lowercase semi-lunate sigma, then you're allowed to turn it into one of these for only 1 point. And you can limit the number of points you get per word so that you don't start just going crazy with edits. You can replace, and most of these are Latin letters that the Greek might get infected with. For instance, uppercase tau is very likely to be misidentified as, uppercase T and misidentified as uppercase tau or even small tau, so on and so forth. Here's an example where we've tried to rank them by making one have a higher score than the other. Uppercase E is more costly. It takes 2 points to turn it into a lowercase epsilon than an uppercase epsilon. Then you get the idea. You score these and then the lowest score wins. And you only get to do so many edits. So that it's kind of like some of those games that people play where you have to change each word and each letter and make a new word and that kind of thing. But the computer does it for us. Finally, once we've got a spell-checked, blended page for each image, we want to see if we can leverage the excellent Latin results that come from Abby Finereader. And we do that by checking if the output from my process, from Rigaudon, is Greek, then we push that into the HOCR output that is crummy Greek from Abby Finereader. This is particularly helpful for texts that have a lot of English and Latin, and in contexts where you want to be able to read this, such as papyrological volumes. A lot of context and then a quotation of Greek. All that process gets done over a matter of hours, and then an email gets sent to me that tells me how well it did. And one of the most important things in that email is an image like this. This is basically a 3D graph of the entire set of results. The pages are along here, and for each page we have a graph with the x-axis being the binarization threshold and the y-axis being the quality of the result. You can see here that the range of binarization thresholds that we chose started with something far, far too light, and then came up fairly nicely to reached its maximum value, and then came crashing down, usually at the point at which the page turns into a big black mess, and then there's nothing there. So we can be pretty confident that we've found the peaks and things around so that each of these pages will be well represented. If, however, we saw something that looked like this, where it just stopped, we'd know that we'd gone a little short, and we probably should do another run and try to get better results next time. And what are those results? Well, the images that I gave you are actually pages that we've worked on, and here's some of the output. There are currently 4.3 million output pages on my web server, so this is not going to be anything like a fair representation. but I hope it gives you the idea that we're getting there, and we're getting there with a number of diverse fonts. Everybody can rejoice over this little baby getting turned into this. It actually turns out it's really easy for the engine to recognize that. What's weird is not always hard. You can also find some mistakes. These aren't mistakes, by the way. This is some artifact of Google's slide process when you go into full screen messes up Polytonic Greek, which I found out yesterday. But there are, let me see, where's the mistake? That's a mistake that you can see there. But we need to leave something for Federico to do. There's some of our other pages. And we've used that Levenstein editor to turn that into that, because it's a very low cost edit. There'd be other ways to do that. You could identify it directly and say, now I was worried that we didn't want to get rid of the lunate sigmas, so I wanted to keep identifying them as such and then edit them out with the Levenstein editor. But there are other ways of dealing with that. All right, so what are we going to do next? Well, the future's to my right. We're going to take the ABI data out of the process. This is the only non-free process in the whole thing. It also means that people can't do this themselves because they'd have to buy ABI Fine Reader, and it's pricey. So with Nick and I go back and forth. He's really helped improve Tesseract's line segmentation, stop it from crashing, which is very nice. And I produced a kind of cleaning process. Often Tesseract's line segmentation is as good as ABI's if we can keep on. And I think we'll get that better and better. So if we can use Tesseract instead of ABI Fine Reader, we can also generate output from Tesseract directly. Nick's Polytonic classifier for Tesseract produces better results than mine ever does on all uppercase words. And so if we can throw the results of that and the results from Orcopus into one big pot and then start the process, we'll have the advantage of 3 completely different code sets working on the same data. And as a result, we'll get much better results because it's very unlikely that the same errors will be repeated by 3 completely different approaches to ancient Greek. Of course, we're asking more of the computers, but happily they're getting twice as fast every 18 months, so who cares? All right, that's as much as I can talk about. If you want to sort of hit me up about something, you might be interested in if you're doing any micro web format stuff. I'm working with Python Flask a lot. All this was done with Grid Engine. And if you're thinking of making bookend images for OCR, please, please, please talk to me because I have strongly held and perhaps even accurate opinions. And this is where our code is, and that's where you'll find those 4 million output pages. And I'll hand the floor over to Federico.
Yeah. So my part is focused on the manual correction. And manual correction on OCR output may be performed by different type of correctors. Particularly, we can have experts that are classicists devoted to the proofreading for a long-term project. This is the approach, for example, that was applied by Professor Mastandrea in his Italian projects on Latin texts. Or we can have data entry firms, which is the issue that they are professional proofreaders, but usually they are not skilled in the target languages. And so they need a comparison of the image of the text and the text that they must correct. Or we can have crowdsourcing, and usually we have students that are learning the target language and that they are not so expert in professional proofreading. And at the end, we can have random volunteers that have an heterogeneous education and heterogeneous skills. So the system for proofreading that I have developed is focused in particular on these 2 kinds of correctors. So professional proofreaders and students. Which are the implications? That we need a system that is centralized. We must manage by a remote server the entire pool of text. That must be easy to use and based on the image-text comparison line by line. It must be optimized to catch the attention on the possible errors that must be distinguished by category because you must apply different strategies to correct them. And then it must efficiently provide the most probable correction. So, the first part is related to the enrichment of the OCR, HOCR files produced by Professor Robertson. As you saw in the previous slides, HOCR is a microformat that is hidden inside HTML files and that contains information about the text and the coordinates on the page. So this system must enrich it with other information. In particular, we need dictionaries with and without diacritics that provide us the suggestions for the spell checker. And if we have at our disposition other editions of the same text, we can align them to the output and use them as a near ground truth. So the ground truth is used to evaluate the quality of OCR, but the ground truth is exactly the typing, okay, of the text that you have recognized. So it is impossible to have a ground truth that is exactly related to the text that you are using. So if we have another edition of the same text, we have something that is similar to the ground truth and that we can align with a lot of philological implications on this process because we have issues to distinguish between real error produced by OCR and, on the contrary, the contamination between the two different editions. And we will see these kind of issues in the next slides. And then we have a syllabic repertory that is a list of possible legal Greek syllables in each position of the word, the initial, middle, and final position, in order to identify well-formed syllabic chains that are possible good Greek words, even if they are not recognized by the spell checker, because we have this variant, this rare variant in the dictionaries that we have created on the previous text that we have at our disposition. So, in order to identify possible errors and provide the good suggestions to correct them, we must spell check the output of the OCR and then process it in further steps in order to classify these possible errors. As I said, the spell checker is based on the dictionaries that are generated on the parsed text collection. So the dictionaries are dynamically growing they grow because we add text, and so we add possible forms, inflected forms that are not present in the previous collection. And we use also an uppercase dictionary in order to evaluate if we have a good character sequence with bad accents or writing marks. The alignment with other editions is performed with a well-known Middleman-Bunch algorithm that is commonly used for the alignment of DNA. And so in this case, we can see the result of the alignment between the OCR output and another edition that is correct. Okay? So in this case, for example, you see that this error, home errors with A instead of eta, is aligned to the word that we find in another edition. So we can see just one example of this possible contamination when we make alignment of with different editions. In this case, Rigaudon, so the software created by Professor Robertson, on the Anecdota Graeca, edited by Kramer, recognizes the word chorus, which is rejected by the current spell checker. Or I should be by the previous version of the spell checker because we have isolated the error. So the spell checker suggests chorus as a correction. And also the alignment with another edition suggests chorus. So the automatic system suggests this correction, and we make the automatic substitution of this one with this one. But it is very important that we signal this automatic correction, because it must be checked manually. Every time that we make an automatic correction by alignment, so not just by spell checking, no, but also by alignment, we must signal it, visualize it with different colors, and the human correctors must be cued in order to verify if it is a good or a wrong correction. And indeed, the page image contains a chorus that is a late form attested from Athenaeus to the Byzantine period, and it is the correct one that we must accept. It isn't just an error on the page. So, the last step is the syllabification. So, in order to prevent the false negatives due to the rare variants ignored by the dictionaries, the system must distinguish between the random character sequences, for example, in particular when we have Greek and Latin characters that are mixed. But not only in this case, also when we have Greek characters that cannot form a syllable, for example, and to do and so on. Okay, so a sequence that is impossible that constitutes a syllable. And as I previously said, I evaluate also the position of the syllable, because, for example, if we have a long sequence of characters and the last syllable contains a breathing mark, it's very probable that it is just an error. Okay, so each potential error is divided in syllable, and the syllable is evaluated according to the position. So, for example, that word that we saw is evaluated as and colored as something that we don't find, that is not recognized by the spell checker, but it is a good syllabic sequence. And so now we can see the web app in action. The proofreader that has a web interface. It is a web application inspired by the Mozilla OCR editor interface, but it employs the Wikisource collaborative philosophy. The OCR editor is very good because it aligns the lines line by line, the image of the text with sequence of characters, but it has two issues. One is that you must work on your version. It isn't, the text is not centralized. And the other one is that you haven't the spell checker integrated with the suggestions that derive from your own dictionaries. On the contrary, Wikisource is a system for collaborative proofreading, but the pages are just side by side, and text is not divided line by line, and you haven't the spell checkers that you can use. The texts are stored in a central XML native database, and so they can be managed remotely. The control panel is very, very simple, so we can select the work and the page on which we want to work, and then we can add the corrections. As you can see, the possible errors and the possible automatic corrections are colored in order to catch the attention of the proofreaders. Here you see, as we have this alignment line by line. This is the image. This is the image of the page, and this is the text that must be corrected. In this way, even if we have proofreaders that don't know Greek, and in many cases it happens when we have data entry firms that work on Greek, okay, and they ask us, please provide us a font that is very, very, very similar to the image, because we must compare the text with the image. In this case, they can see that this sign is different from this one, and so they can correct it. The cues that we want to provide to the correctors are, in particular, this one. When we have wrong accents and writing marks, the attention is focused on the diacritics. When we have self-corrections, we need special care to avoid the risk of continuance. And in all the other cases, we must focus the attention in many directions. Here we can see an example of these classifications of errors and self-corrections. we are not too aggressive with self-corrections, because we evaluate, first of all, if it is refused by the spell checker, if the edit distance is very close, okay, and if it isn't a well-formed syllabic sentence. In these cases, the substitution is automatic but colored. Okay, and this is this self-correction. These self-corrections are very important because you gain a lot of time if you make the substitutions automatically, because the corrector must just compare, verify, and nothing else. Didn't need to make an action to change the text. When the corrector must perform a correction, he just selects the word, and a combo box appears with the suggestions provided by the spell checker, and if some solutions is provided by alignment, it is marked with a particular sign. In many cases, it is the correct one, but as I previously said, not in every case it is substituted automatically. Okay. In this case, for example, we have a suggestion provided by alignment that is also a good suggestion. Okay. The dictionaries are rebuilt. So when we receive the corrections by professional people, so when we are sure that we have very good corrections, we rebuild the dictionaries in order to augment them, in order to have new inflected forms that will be used on the next text that we go to correct. And now we see the future, what we are working on. And the big issue is the identification of the false positives. Because if we have false negatives, no mind, we just lose time to be sure that it is a good solution. No? It is colored, we check, we see that it is good, and we accept it. We have lost just time. But when we have false positives, we have a philological problem. And if we don't correct it, then we have a bad accuracy. Okay? So, how to work on false positives? This is our future work, no? So, by definition, the false positives pass the spell checking. So they are not colored, okay? And especially if they are graphically similar to the correct word. For example, when we have a delta and omicron with a bracket mark in Greek, or an M and NI in Latin, they are difficult to be seen, they are difficult to be recognized. In particular, if the proofreaders are not skilled in the target language. So, a new approach can be used to identify them, and it is by alignment of text that are supposed to be correct, okay, and translations in modern languages. This is a system that was developed by David Bauman at the Persis project. He applied it extensively to English, and I applied it just on a few texts on Italian language. But the application to many languages is very important because we can process this information. And processing this information, we can then combine this system with the new WordNet that Harry Diakov and I are developing for ancient Greek, and we are searching to extend also the Latin WordNet that was developed in Verona. So, what happens in this case? You don't see here, but here it's written quorum vini atque naturam, and so on. Okay? So, somebody that's skilled in Latin just just see that something is wrong. But somebody that doesn't know Latin could be deceived by this vini, okay? Because Ni is very similar to M, okay? But what happens if we align with the Italian translation? That we have an alignment between this enigmatic vini and efficacia, that means efficacy. So, something is wrong, and we can capture it with the evaluation of the semantic distance, because between vinum and efficacia there's a very large semantic distance. On the contrary, between vis and efficacia there's a semantic distance that is equal to 0. Okay? So, this isn't vini, this is vim. Okay? That means many things, and it's also efficacy, okay, power and so on, virtue and so on. So, with the ancient WordNet that contains the Greek and the Latin WordNets, the synsets have been extracted from the bilingual dictionaries. So these groups of synonyms. No, we are working on it now. We must apply a lot of filters to the current results that are a little bit dirty due to polysemy of the English language. Because when you have a Greek word that is translated by an English word, you can collect, when you have many Greek words that are translated by the same Greek English word, you can collect them in a synset. But if this English word is polysemous, you put together words that are not related. For example, if you have the English word sound, you put together words, Greek words that have the meaning related to sound, but also to health other things. Okay? So we must work on it. And the words, all the WordNets are aligned to the Princeton WordNet, and so we have an alignment of Latin and Greek WordNets to modern languages such as the English, Italian, and French, German, and so on. So we can use them. In conclusion, we see that the system, this web application that we use for proofreading, is based on the features of other applications, but that we need to put together for our purposes. And I am very interested to say that the entire workflow is circular. So at the very beginning we have the training of the OCR, and then we perform it, we make the spell checking, we correct the texts, but we enlarge the dictionaries, and also when we have the corrections, we can retrain the OCR, because we preserve also the coordinates of the single characters. And so if we are sure that we have a text that is corrected accurately, we can retrain it. And in this case, we have the real ground truth. Mm-hmm. No? The result that we collect from this process of proofreading provides us a real ground truth that we can align to the different outputs, and so we can evaluate which are the most frequent errors. And so the table that Professor Robertson showed can be improved automatically. The table with the frequent errors will be improved automatically, because we have the very correct text and we have the original OCR output. We align them, and we can have a new system that is better than the previous system. Yeah. Okay.
Thank you very much. Okay, the floor is open for questions. Nick.
Can you, the false positive thing you were talking about, with the semantic difference, I think I just missed something you said. I didn't understand where the Italian, efficacia, so I don't know Latin.
So this means of wine. And the other word VIM is...
Yeah, because vim is the accusative of vis, and vis means virtue, but means also efficacy. Okay, so in our Latin wordnet, we have synonyms of vis, okay, that are perfectly aligned to English words and also to Italian words that contains also efficacia and in English efficacy. So if I search for vini, so first of all I must lemmatize it. So from vini, that is the genitive of vinum, I have vinum. Okay, vinum is in synset related to a concept that is wine and something. So okay, so totally unrelated with these kind of words. Okay. On the contrary, if I search,
where did the efficacia come from?
From the alignment of the entire Latin text of De Divinazione. This is the De Divinazione by Cicero, by Cicero, okay, and the Italian translation with the Bauman's system that aligns bilingual texts. So you have an original Latin text, you have a modern language translation, and you must provide a list of correspondence between inflected forms and lemmas, and automatically it aligns one term with another term, or one term with a phrase, or one phrase with a single term. Okay. In this case, for example, you see that I must say that it is really serendipity, because I used this example for other purposes. I was very fascinated by the fact that the system is able to align mirari licet with è lecito constatare con lieta meraviglia. So licet è lecito, and mirari is aligned to constatare con lieta meraviglia. Okay. The system is a stochastic system, so it evaluates the possibility that some words are aligned to some other words. It works with the frequencies of anchors. Okay, and so if something is between two anchors that are aligned, is a little bit compressed. And this is the reason that it is able to align a good translation with a mistake in the original language. Magic system, it is just a system that is able to find a good translation of very frequent words. So, for example, here you see that vulnera is correctly aligned to le ferite, and ratio is correctly aligned to ragione. Okay, this one is a bad alignment, but it is a good alignment with the true version. So our future purpose is to see this type of inconsistencies and to signal them, to color them in some way, because if you have many translations in many languages of this text, and in this position you find efficacia in Italian, efficacy in English, and other words that are related to the same concept in other languages, you have an evidence that here something is wrong, something must be corrected. And last, I was not surprised, but I was impressed by the fact that if you search on internet this text, you find a lot of times this text with this error. Okay? So if you want to evaluate, obviously you must have the paper in front of you, or actually a digital image that you easily find on archive. Okay? But you need the evidence of the image to check it. Okay? Otherwise, you for this specific case, just a little bit of the Ignazio is enough to solve the case. Okay.
What do you do with texts in different Greek dialects? For example, is a Doric genitive going to come?
Yeah, this is very important. Yeah, this is very interesting. It depends by the dictions, because as I said, the dictionaries are based on the current corpus. So if we have the specific forms in that specific dialect in the previous corpus, it recognizes it. Otherwise, it just generates false negatives. Okay, that you must check manually, and so the next time you will have this form, and you will have a better dictionary also with Doric forms, for example. Okay.
Very small question about the pipeline that Bruce was describing. There's a couple of very small things I wondered. We talked about the part that was doing weighted edits and this sort of thing, and was comparing so against the spell checker and various other ways of parsing, looking at the text and seeing whether it needed correcting and so forth. Is in that pipeline, is there a, well, two questions, I guess. In that pipeline, is there anywhere a tool that looks at the current attempt to interpret the word, and regardless of whether the word is recognized, regardless of whether the word is possible, does, for example, sees whether the accentuation would be possible according to the Loeb rules of accentuation of Greek, for example? It's a very simple test one could do. I remember doing the TLG had a software that would do exactly that test. And another question is, does the spell checker check against a dictionary, a massive dictionary of exact forms, or will it also attempt to parse a word by looking at various endings, looking at various prefixes that can be attached? I remember again at the TLG we used to do this a thing that checked against exact forms, and we would, in almost every text, especially when looking at medieval texts, we would find words that weren't recognized, that were instantly recognizable to the human eye. They were just, you know, passive aorist optative with 3 prefixes. Yeah. Something had never occurred before, but was of a perfectly well-known word. So either of those tools, things that you have in your
so the answer to the first question about sort of legal sequences of accents, that would be subsumed under the Boschetti score. So that's now that doesn't reach to the level of spell check. That's in the early evaluation of the page. Ideally, when we're doing word by word substitution, we've been pitting words against words by finding if that word's in the dictionary. Again, in the earliest stage of things, in what I call the blending process. I think it would be better to do that by the Boschetti score for each of those words, and then what you were describing would be done at a much earlier level. We'd get the best word that gets the word that gets the best score, even if it isn't a dictionary word. Up the pipeline in the spell check process, it's a flat dictionary of about how many million words? Do you remember?
So it is 1,002,000 inflected forms, right, with emphasis, accents, and so on.
Yeah.
So, yeah.
So, and then I think there's another one that takes the accents out and then compresses it, so they're unique forms. I think I've added to that though, because I have a lot of personal names that I extracted from somewhere else. So it's probably about 2 million.
Yeah, because we have 2 sources. We have words that are extracted from the corpus.
Yeah.
And they are more or less 400,000.
Yeah.
400,000. And in this case, we have also proper nouns and so on. And then we have a complete database dump made on Morpheus that generates inflected forms.
The weighted Levenstein approach, though, is extremely atomic. It's about substitutions, replacements, and additions and subtractions, and they could be you know, cups in a row. They could be anything that you're doing that with. So we need to use decomposed Unicode. As a result, there's whole classes of errors that won't get dealt with. If you have an iota with a cute accent that gets misidentified as capital I, there's really no way you can Levenstein your way out of that, unless you were to do a second tier of Levenstein editing with composed. So you'd start with decomposed and then do composed. However, yeah, I'm not sure I believe, you know, at that point you're just trying to kind of nuance something. The approach with Levenstein, though, is to try to avoid a whole bunch of grepping your way to success, right? Going, well, it often makes a mistake of these two, so I'm just going to go through, and this is sort of more systemic, more atomic, and meant to be more rigorous. There are other editing algorithms that are particularly used for spell check, where people are likely to type, like swapping is another edit that you can make in these other ones. But I came to the conclusion that swapping wasn't a likely mistake in OCR.
And it's remarkable that Gamera decomposed the fonts, and so it recognizes independently the character and the accents by the marker.
Unless they become a connected component. Unless they get glued together, and then usually it recognizes.
And then it's glued together. On the contrary, Tesseract works in a different way, and it recognizes it in an holistic way. So this is one of the reasons that even if we work on the same text, on the same image, page image, different engines provides different results with different error rates, character by character. This is the reason that we can have this approach of merging the results of the different engines.